Okay, welcome to our talk, All You Ever Wanted to Know About the AMD Platform Security Processor and Were Afraid to Emulate. In this talk, we present PCB-EMU, an emulator for the AMD PSP. So this is Alex here, and I'm Robert. And Alex is doing his master thesis at the Technische Universität in Berlin, and I'm his supervising PhD student. Today, I'm going to talk about the Platform Security Processor and what it's used for, and why we would want to emulate it. And then Alex will tell you about how we emulated the PSP and what you can do with the emulator. So let's start with a brief overview on the AMD PSP. So this is a slide I've took from an AMD slide deck. And the AMD says here that the AMD Secure Processor is an integrated microcontroller integrated into the x86 SoC. It is an ARM Cortex F5, and it is present on both EPYC and Ryzen CPUs. Actually, it has been integrated since 2013, but for our talk, we only concentrate on the PSP of Zen and later generation of AMD CPUs. So it runs an undocumented and proprietary firmware provided by AMD, and the PSP is the root of trust for the whole x86 SoC. So why would we want to emulate this device? Well, it runs privileged software at a very high privilege level. It is the root of trust. And we can statically analyze its firmware, but that is time consuming and from my point of view also a bit boring, and it's only good for a single firmware version. If at one point in time AMD decides to completely rewrite their embedded firmware code for the PSP, we would have to start over again and analyze the binaries. However, if we would be able to emulate the PSP itself, we could just execute the emulator with the new firmware and analyze it at runtime, which is way easier than plain static analysis. Now, before we start writing the emulator, we need to have the firmware. And the AMD PSP firmware can be found within the padding of UEFI images. So if you download an UEFI image update for a motherboard, you will find a padding section, and within that padding section, you will find the PSP firmware code. And the PSP has its own file system, and we wrote a tool called PSP tool, which you can use to dump the content of that file system. I'm not going to go into details about this file system during this talk, but you can have a look at our previous talk, which we've given at the Chaos Communication Congress back in 2019, where we explain more about the firmware file system structure and a little bit of background of the PSP. Today, I'm going to talk again about how the PSP boot process is working. As I said, the PSP is the root of trust for the AMD SoC. So the PSP actually boots before the x86 cores. And on the PSP, there is a component called the on-chip bootloader, which is the first component which boots. And the on-chip bootloader is a bootloader which is embedded in read-only ROM memory. Now, the responsibilities of this on-chip bootloader are to load and verify an off-chip bootloader, which is stored on the SPI flash. Now, if the binary of the off-chip bootloader could be verified using a public key, the off-chip bootloader is executed, and the off-chip bootloader will initialize the system. And to do so, it will load various applications in a static order. And from these applications, you can see that there is an ABL0 stage, which has embedded multiple ABL1 to 6 stages. And these are the stages that actually configure and initialize the x86 SoC. And this includes the training for the DRAM, for example. When this is finished and DRAM is available, the PSP will load and verify an UEFI image into the DRAM and then release the x86 cores from reset. And only now the system or the main x86 cores boot up. Now, on the EPYC server variant of AMD CPUs, when the system is fully booted, and we have, for example, Linux running on the x86 cores, Linux can issue a request to the PSP, which will then load the firmware for the secure encrypted virtualization technology from AMD. Again, I refer you to our previous talk if you want to have a bit more background or details on this part of the AMD PSP. Now, if we look at the Ryzen CPUs, the boot process is somewhat similar, except for the last step. When the x86 cores are released from reset, the PSP will overwrite its own SRAM memory with another operating system. And this is the Secure OS, which is provided by Trustonic. It's a KINIBI TEE. And the whole SRAM is replaced with that operating system. And this OS is responsible, for example, to host a firmware TPM. So if you have an AMD mainboard and there's an option to use a firmware TPM, that firmware TPM is actually running on the PSP. Now, the Secure OS will divide the PSP again into a non-secure and secure side using ARM TrustZone technology. So much for the boot process. Let's have a look at the hardware of the PSP itself. Now, the PSP, as mentioned, is an ARM Cortex-A5. So that means it has a 32-bit address space. And at the top of this address space, or at the bottom, depending on the way you look at it, we have the local SRAM. And the SRAM is either 256 kilobytes or for Zen 1 CPUs or 384 kilobytes for Zen 2 CPUs. And this is the whole memory which is used to store and execute the off-chip bootloader and all its applications. Now, at the ARM High Vectors page, at the end of the address space, we have the ROM bootloader. This is present at a fixed memory location, and this is the start of the boot process. Now, in between, we have a dedicated MMIO region, which contains various devices such as an IQ controller, a timer, a crypto accelerator, and x86 and SMN slot controllers. And the rest of the memory space is essentially divided between the SMN, so the System Management Network slots, and x86 slots. So what are these slots? A slot is a view into another address space. And this is required because the PSP has not only access to its own address space, but also access to various other address spaces. So the PSP has access to the System Management Network. This is another 32-bit address space which has various devices present. So for example, the memory controller of the x86 SoC is part of the System Management Network. And when the PSP wants to configure encryption keys for the memory controller, it will talk to the memory controller via the System Management Network. And we can also find some fuses there, and the SPI flash is also part of the System Management Network. Now, this System Management Network is completely undocumented, so there are probably a lot more various devices there which we have not figured out yet. Now, the PSP has access to this address space, and the way this works is that the PSP one can map certain parts of this address space into its own address space. So, for example, if it wants to access this green part of the SPI region, it will tell a dedicated controller within the MMIO space to map this region into its address space as a fixed slot. So the hardware then will ensure that the same system management region as configured is visible within the PSP address space. Now for x86, there's a similar mechanism. The x86 address space is 48 bits wide, and it's partially documented. You can Google for the AMD processor programming references, and they will yield some information about various devices which are present in the x86 address space. And the PSP has access to all of them, using the similar mechanism as explained previously. So for example, the PSP can access the complete DRAM by mapping parts of the DRAM into its own address space and then performing a simple read operation. Another interesting device which is present on the PSP itself is the crypto accelerator. The PSP has a cryptographic coprocessor version 5, or CCP. This crypto accelerator has support for various algorithms such as SHA, RSA, AES, ECC, zlib, or even provides support for true random numbers. Now, the PSP makes extensive use of this device, and it also uses this device as a simple DMA copy engine. It uses it also to verify signatures or to decompress firmware files. There is no official documentation available for this device, but there's a Linux kernel driver. And this is extremely valuable for us because that allowed us to really understand how the PSP performs certain actions such as signature verification or decompressing binaries. Now, Alex will continue and talk about how to emulate those devices I just told you earlier about.
Thanks, Robert. So how did we approach the actual emulation? Well, the easiest approach, of course, is to just start executing the firmware and see for how it gets. For that task, we have chosen Unicorn because it is an easy-to-use API, and we thought it is perfect for that kind of task. So at some point, the firmware will hang or Unicorn will throw an error because an unmapped region is accessed, for example. We then analyzed the fault and the code which was executed before, trying to make sense of it and get an idea what the emulator was missing. At last, we've implemented and debugged the missing functionality and then started at the execute step again and continued with the next round. This approach brought us pretty far. So after about 2 months, the emulator was able to execute the on-chip bootloader we've gathered from various CPUs previously, and the on-chip bootloader was able to load and execute the off-chip bootloader from the emulated SPI flash using the emulated cryptographic coprocessor. The off-chip bootloader was also able to load and execute the first 2 applications. We, as of today, still don't know what they're actually used for. This required working signature checking, zlib decompression inside the CCP, among other things. The off-chip bootloader also started executing the base AGESA code for bootstrapping the whole platform, but at this point, the code was hanging trying to communicate with some device. There we had to stop with our so far successful approach because trying to emulate all devices to some extent would be a daunting and almost impossible task without knowing anything. Just think of possible side effects certain accesses might have on other registers and devices in the system. Here you see a part of the trace from the emulator for an emulated run of the firmware. The PSP has a register in MMIO space, which is used by the firmware to store postcodes to it when it reaches a certain point in the boot process. And you can actually see that it successfully started up, that it read and initialized data from the SPI ROM, and also that it executed the first 2 applications, the debug unlock app and the security gasket application. And the last status you see here is that it also started loading and executing the AGESA 0 application. So we had to choose a different approach, and because we already had code execution on the PSP for quite some time, we quickly came to the conclusion to leverage that and try to pass through hardware accesses the firmware makes from the PSP emulator to the real hardware. For that, the real PSP will run a stub, forwarding those requests from a generic proxy component in the emulator. This component will capture all accesses to regions which are not being used by configured emulated devices, like the emulated flash, for example, and forward it to the stub running on the real PSP, where it communicates with the device and return the result back to the emulator. Robert will talk about the vulnerability we've exploited a bit later on in this talk. So proxy mode was born, but the biggest question was the communication channel to use, as the whole system wasn't initialized when we wanted to take control over it, which is right after the on-chip bootloader tries to hand over execution to the off-chip bootloader. So not even a simple device like the serial port was working, and because the whole system is still mostly black box to us, was making it even more difficult. So the only interface we knew about and had access to was the SPI flash interface. The PSP contains a flash controller which maps the content of the SPI flash into the SMN address space, and if the PSP firmware reads or writes to or from the SPI flash region, it will generate the necessary SPI commands on the SPI bus. So the university bought an SPI flash emulator which was hooked up to the system. The good thing is that it also has an open source utility to configure it and read the SPI trace later on, so we could modify it. The idea was to let our stub read or write a magic location in the flash area, which then the controller translate to the necessary SPI commands, and the flash emulator would then capture. The tool on the host would then read out the trace, parse it, and extract the data inside the data when it recognizes the magic location. The extracted data would be then made available over a simple network socket to a PSP emulator. Likewise, it would also take the data from the socket and reprogram the flash so the stub has access to the data when it tries to read it. This sounds simple, but was made complicated by the flash emulator itself because you have to disable SPI emulation on the flash emulator when you want to update the content of the SPI flash image in RAM. Which is obviously a bad idea if the stub is accessing the flash at the same time. So we had to put some sort of locking protocol on top of it to prevent the tool from disabling the flash emulator at an inconvenient time when the stub is actually accessing the flash. The problem here is that everything got rather slow. We had a stable communication using that method, but we could only do 2 to 3 register accesses per second using this method. For example, it took about 20 minutes for the on-chip bootloader to complete its run in the emulator, even though it wasn't accessing a whole lot of regions inside the SMN or MMIO address space. So, and it of course still requires an expensive flash emulator. At this point, we started looking into getting the UART initialized and working, so we had something hopefully faster and not requiring an expensive flash emulator. Robert already mentioned that we then came across the processor programming reference manuals, which are freely available for everyone. And in there, we found a description of a low-level SPI controller interface, allowing the BIOS or UEFI on the x86 side to send arbitrary commands to the attached SPI flash. We've also found some code in the PSP firmware earlier, which we thought would do the same, but we were never able to recreate it in our stub to execute arbitrary SPI commands. So with the described SPI flash interface residing in x86 MMIO space and the SMN address from the PSP firmware, we hope that the register interface described for the x86 side is actually just the same than what's behind the SMN address. And it actually worked. So now we were able to send arbitrary SPI commands directly to the SPI flash, which enables us to use a communication side channel inside the SPI flash emulator. So we could exchange data at a much greater speed than previously. So after implementing a proper transport packet in our stub and modifying the flash emulator tool to forward the data using the side channel, we had a really fast and reliable communication channel to work with. It, however, still requires an expensive flash emulator, unfortunately. So to put this in perspective, with running the off-chip bootloader inside the emulator, it now took only about 5 minutes for the complete bootstrapping process to complete, whereas before only the on-chip bootloader would already take over 20 minutes. So because we still need an expensive flash emulator and we wanted to make it easier for others to fully use our code, so we still wanted to get the serial port working. It would be much slower than the SPI channel, but it would be a very low-cost solution. Legacy serial ports on almost all consumer mainboards today are handled by a so-called Super I/O chip, which sole purpose is to provide legacy I/O like a keyboard, mouse controller, a parallel, and serial ports, among others. And these Super I/O chips are attached via the so-called low pin count bus directly to the AMD SoC. However, these Super I/O chips need to be configured to enable serial ports, and the configuration sequence depends on the chip being used. This is usually done by the BIOS or UEFI firmware. And to complicate matters, most of these chips, like the ITE one on our mainboard, have no public reference manual, so we had to get at the initialization sequence for the UART somehow. For that, we hooked up a logic analyzer to the LPC bus and captured everything going on there using the stock firmware image. The resulting capture file was then processed by a self-written tool called LPC decoder to make analysis easier. After extracting the necessary sequence from the capture and implementing that in our stub, however, the UART was still not working. And after a lot of trial and error, it turns out that one has to flip a single bit in a register living in the system management network space to either turn on the Super I/O chip or bring it out of reset. But with that in place, we also now have a slow but low-cost solution to communicate with the code running on the PSP before the platform is initialized. However, depending on the Super I/O chip being used for a particular mainboard, one might have to adapt this initialization sequence a bit. So, and before continuing with the an overview of the PSP emulator, I will hand back to Robert, who will talk about the security vulnerability we've leveraged to gain actual code execution on the PSP.
Okay, thanks, Alex. Now let's talk about how we can inject our own stop code so we can use the proxy mode. Now, as explained previously, when the PSP boots up, the first thing that's happening is that the on-chip bootloader is executing. And the on-chip bootloader is executing from non-writable ROM memory. So that means before the on-chip bootloader can do anything, it needs to map certain parts of the address space for its stack. And that's what's happening. So part of the SRAM now is reserved for the on-chip bootloader stack. And then we need to load and verify the off-chip bootloader, which is stored on the SPI flash. So then the next step for the on-chip bootloader is to map the SPI flash. And then the on-chip bootloader will load and verify an AMD public key, which is present in the SPI flash. The public key is placed into the SRAM. Once that is finished, the on-chip bootloader will load and verify the off-chip bootloader. The off-chip bootloader is part of the SPI flash, and it will copy the binary into the local SRAM. Now, you can see that there's a red line between the off-chip bootloader and the bootloader stack. Of course, this copy operation must not cross that line. So we have a certain maximum size that the off-chip bootloader can occupy, and this size is smaller than the SRAM size. So the on-chip bootloader needs to validate the size of the off-chip bootloader before the copy operation takes place. Now, how do we get the size of the off-chip bootloader? Now, if we look at the firmware file system, we see a structure like this. We have directories and we have entries in directories, and these entries point to files. And the off-chip bootloader is one of those files. And each file has a header, a body, and a signature. Now, if you look at the header content, we see that there are two different values of interest right now. So first of all, at offset hex 14, we have the body size. So this is the size of the off-chip bootloader in the SPI flash. And then we have a load address. And this load address is the target where this off-chip bootloader wants to be placed in the SRAM. Now, the on-chip bootloader needs to copy the off-chip bootloader into the SRAM, and only then its signature can be verified. This is because the on-chip bootloader must avoid any talk-to attacks, where the attacker switches the content of the SPI flash, for example, after it has been validated. So this header I talked about is processed before the signature check is validated, or the signature check is carried out. So that means the on-chip bootloader needs to validate the header values carefully. So let's have a look at the function that does this validation. Now, first thing the on-chip bootloader does, it compares the load address from the header plus the body size, also from the header, against a fixed threshold, which is the start of the bootloader stack. But it does not take the values as they are stored in the SPI flash. Instead, it takes the absolute of those values. So it masks out the sign bit, the highest bit. So if we calculate now this value, you see that we have an absolute of hex 100 plus the absolute of hex C640, and the result is C740 in hex. And if that value does not cross the beginning of the bootloader stack, we can safely place the off-chip bootloader here. Now, the copy operation that's doing this actual copy part looks like this. So we copy to the load address from the SPI source address, and we copy body size times size. Now, let's have a look at those values. You can see for the check, we use the absolute body size. However, for the copy operation, we use the body size as is. So that means, let's say we take the body size in the SPI flash and we flip the highest bit, making it either a negative number or very large if interpreted as an unsigned integer. Now, if we do the check again, we see it calculates to the same value. So it doesn't matter if we flip the highest bit for the security check. The resulting value is still small enough for the copy operation to take place. But the copy operation actually uses the size as is. So we have now a mismatch between the size that it's validated and the size that is used for copy. And actually, this size now here is way larger than the whole SRAM of this PSP. So if we use that copy operation right now, we would copy over the whole SRAM content of the PSP, including the on-chip bootloader stack. So let's do that to insert our stub. So we place our stub within the SPI flash, and we append it with return addresses. And these addresses start to the beginning of our stub, point to the beginning of our stub. Now then we flip the sign bit of the body size, and the resulting copy operation will happily copy over the whole SRAM. And the data which is copied is our data which we put into the SPI flash. So that means in the end our stub is copied into the SRAM. The return addresses or the whole stack of the on-chip bootloader is replaced with our return addresses, which then point to our PSP stub. And as soon as the copy operation inside the on-chip bootloader returns, we execute our stub immediately. And this all happens before any signature is validated. So that means the fact that we cannot create a valid signature for the PSP stub doesn't really matter at all. Now, if we use the same setup inside the emulator, you would see something like this. This is an output of the emulator which shows the CCP requests. This is the copy operation which I talked about earlier. Now, the PSP firmware uses the CCP for larger memcopy operations. So in our case, when copying the off-chip bootloader from the SPI flash to the SRAM, not a simple memcopy is used, but the CCP is used to copy the data. And this is the printout of the corresponding request. And here we can see the CCP request uses a very large size value to copy the data, and the target address is a low address into the SRAM. This is the target address which is specified in the SPI flash, in the header of the off-chip bootloader. Now this way we can insert our own code directly after the on-chip bootloader executed. Now, to summarize this feature, we've tried this on several systems, and from the best of our knowledge, all Zen and Zen Plus CPUs are affected. We confirmed this on Ryzen 1700, an EPYC 7281, and a Zen Plus CPU, it's a Ryzen Pro 3500U, and a Ryzen 5 2600. We've looked at Zen 2. We don't think it's affected, but we don't know for sure, actually. Of course, we reported this to AMD. We reported this in end of February this year. And, well, it took some time for AMD to respond at all. So they responded in the beginning of May. And what they said was basically, all right, this is a known bug. It has been reported by others. So we're obviously not the first one to discover this. And they have developed mitigations in various products where appropriate. So I don't think there's any meaningful mitigation besides replacing the actual hardware, because this is a bug in the ROM bootloader code. But what do I know? Maybe AMD has some magic that actually fixes this. Now I'm going to hand over again to Alex for you to show you how you can use the emulator to analyze your own firmware, which you downloaded maybe from a motherboard update.
So next we will go over the most basic command line arguments and features you will encounter when working with the emulator yourself. So first you have to set the starting point in the boot process where you want to begin emulating. The shown example starts executing the on-chip bootloader. But we also have modes to execute the off-chip bootloader or even the secure OS directly. The second argument selects the flash image to use for the emulated SPI flash image. And as we've selected to start emulating with the on-chip bootloader, we also have to load that one as well. If you decide to start with the off-chip bootloader or the secure OS, you have to use different arguments to load that one into SRAM. Then you set the destination of the trace log. So everything which is deemed important by the emulator will be logged to the trace log, like I/O reads and writes and so on. And because most of the time it will be interesting to see the interaction between the various user mode modules and the supervisor mode code, you should also enable syscall tracing. So every syscall being made along with its arguments will be logged to the aforementioned trace log. The last argument in this example will enable the GDB stub to listen at the specified port. So you can hook up GDB to the PSP emulator and then use breakpoints and watch points to control the execution of the loaded binary and analyze it. So this is a basic workflow of when using the emulator. Next, I will give a brief overview about the architecture of the PSP emulator. So at the core, we use a heavily patched unicorn, which gets wrapped by our own PSP core abstraction layer, which takes care of MMIU-related things, handling SVC calls from user space, like doing the transition to supervisor mode code and back, for example, and other stuff. Because it turns out Unicorn wasn't made to be used as a complete system emulator after all. Then the PSP IO manager handles all MMIO, SMN, and x86 accesses being made from the firmware and forwards them to the appropriate devices. Therefore, it emulates the SMN and x86 slot registers Robert already talked about in the first part of this talk. Everything is then wrapped by the PSP CCD component, which represents a single CCD and therefore PSP instance in a real system. Below all that, there is a tracing component, which is responsible for generating the trace log and capturing information about I/O reads and writes and SVC calls, for example. And our debugging component is based upon our own libgdb stub, so you can debug the firmware with GDB or even IDA Pro, for example. And if you have written your own code, you also get source-level debugging for free. We've used that to debug certain parts of our stub and for debugging the exploit, for example. It also gives access to special commands when using GDB's monitor command. So you can access certain features of the emulator, for example, to read or write to devices on real hardware when proxy mode is used. The proxy mode component is based upon libpsp proxy, which gives access to the real hardware using the aforementioned methods like the UART or SPI flash emulator. The GDB monitor command also gives access to the built-in coverage tracer. So the coverage tracer generates coverage traces of either the complete run of the firmware or just a certain part of the code you are interested in. And the coverage trace is compatible to the RCOV and can be loaded into Ghidra, for example, using the Dragon Dance extension. And also recently, PSP-EMU gained the feature to record all I/O reads and writes into a certain log file and replay that later on. So you can recreate a specific run of the firmware when you don't have access to the real hardware. And with that, our emulator can already do quite a bit. For example, what we can do is bootstrap the real hardware when in proxy mode, up to the point where DRAM is initialized and the UE5 firmware starts executing on the x86 cores. However, the UE5 firmware will then detect an error and will go into a recovery mode and won't continue with booting the system further. And also, this is all for a Ryzen 1700X, which is first gen Zen, and we didn't try that yet on Zen Plus or Zen 2 systems. Also, CPUs which have multiple CCDs and therefore multiple PSPs won't work right now. But we also have the stable communication channel with the PSP for further exploration. You can use the UART or the fast SPI flash emulator. We also have a basic toolchain for writing and debugging your own code running on the PSP. And the I/O log record and replay feature doesn't require access to real hardware for first steps. Last, we also have a basic MicroPython port which runs on the PSP. So all the Python fans out there can run Python on an embedded ARM CPU inside their AMD CPU. So we still have a lot of room for improvement though. Our final goal is getting the real hardware to fully boot using our emulator. For that, we have to understand SecureOS on Ryzen and getting it to run properly in the emulator. Also, for most CPUs, we have to emulate multiple CCDs and PSPs, which also requires support in our stub to handle that on real hardware as well. And we also want to investigate SecureOS further, looking for more security vulnerabilities. Also, what we want to get working is the emulator working with Zen Plus and Zen 2 systems. And last but not least, Zen 3 is about to be released end of this year, and we will see what kind of surprise it brings with it. So if you are now interested in getting yourself familiar with the emulator and want to run your own code, here are all the main repositories of the components required. Everything is either MIT or GPL. And with that, we thank you for your attention and should hopefully be open for questions now.
Hi there.
Hi. Just a quick status update before we start answering questions. So because the talk was pre-recorded, we had some time to develop the PSP emulator further. And right now, we also added a mode where we can run the UEFI image, for example, inside of VirtualBox and forward all the x86 hardware accesses through the PSP emulator to the real hardware. So we can also examine the UEFI firmware and how it interacts with the PSP.
So feel free to ask any questions if you have.
So for the question, is a proprietary operating system running in PSP? The off-chip bootloader is, so everything is proprietary. The off-chip bootloader is not a real operating system in the usual sense because it has no scheduling and no virtual memory and memory protection features as you would normally find in an operating system. The Secure OS on Risen is Kinibi, so it is a full-fledged TrustZone-based operating system, but we couldn't have a deeper look into it right now. So, okay. No questions. The on-chip bootloader we got through the security bug, which we explained in the Chaos Communication Congress talk from last year. And we got into it using the off-chip bootloader, and then we're able to just read out the the last 64 kilobytes of the 4 gigabyte address space to get at the on-chip bootloader, because there's apparently no protection there against reading it.
So yeah, the presentation was started, I guess, probably 10 minutes too early. So that was a technical issue, and sorry for that. The talk will be available on demand. So if you want to get into the first 10 minutes or so, you can find them later on. The Cortex used inside the AMD CPU is a Cortex A5. So when the PSP is booting, it won't make use of any TrustZone features at all, so that was not an issue for emulation. Of course, later on, when the secure OS takes over, that one uses the TrustZone features, and that was some technical problems that we had to overcome, because our emulator is based on Unicorn, and it's not made to be a full system emulator. Not sure what you mean by work with AMD. I mean, we reported the issues we found, but that's about it. We didn't have any further contact with AMD regarding our work.
So regarding the proxy mode, it accesses the PSP emulator through the SPI flash interface. Currently, we have an SPI flash emulator, which also has a feature called hyperterminal. So you can essentially exchange data between the SPI master and the SPI flash emulator itself. And that is used as the communication channel. Because the PSP also has access to the x86 device and MMIO space, it also can access the legacy UART. So we can also use the legacy UART and serial port to access the stub running on the PSP itself. Ich kann mal kurz nach.
Yeah, the talk was run 10 minutes too early, so it's not your fault that you missed any of it.
Yes, we are still using the emulator right now because it's much faster. So using the emulator to get to the initialized DRAM stage, it takes a bit over 5 minutes, and with the serial port, we have already almost 45 minutes. And so the flash emulator is much faster if you change something than to test it. But the serial port is as stable as the flash emulator, because there are apparently no critical timeouts during the initialization stage of the off-chip bootloader.
So for Zen 2, the overall firmware structure is essentially the same. It looks like it's the same code base as used for the first generation Zen, but the AMD tightened up the security a lot, so there are not too many issues. For example, for EPIC systems, we did not find any exploitable security issues so far. For Ryzen, it's a bit different. There are some issues, but not that many as we found in the first generation Zen CPUs. Overall, the security measures are much harder or much better implemented by AMD than for first generation Zen CPUs. But the firmware itself is pretty much the same.
Okay, so because the poll closed and there were two persons who said that they want to see a demo, I hope you can see my screen right now. So what we have here is the emulator itself running with all the arguments required. So what we will showcase is our exploit taking over the PSP, in this case the emulated PSP, and executing the PSP stuff. Below you have the GDB attached to the emulator, and on the right hand side you will see the trace log, which is generated while the emulator executes the code. And we set a breakpoint to hex 100, so that is the off-chip bootloader entry point, and we will just go with continue. And then at some point, you will see a lot of output, which is a bit garbled because you need a bit wider of a window for that. But you see here below, we are in our code. We can then set a breakpoint to the main, for example. So then it will execute. It's a bit slow because it's single stepping. Okay, so and now we also have source code debugging. We can do next, for example. We can show register. Sorry, not show. Info registers. We can see the call stack, and then we can evaluate the firmware. So with the normal firmware, you of course have no source code access, but you can step through the disassembly and so on, and do all kinds of things like changing registers and changing memory. And we also have quite a few special commands for the debugger, which is accessible through the monitor GDB command which is specific to the PSP itself. So, and if you're on proxy mode, you can also have a lot of a few more commands. Then you can, for example, from GDB access the SMN network directly, or MMIO space, or the x86 address space on the real hardware itself. So, maybe this is what was also shown in the presentation. So this is where our exploit kicks in. When the on-chip bootloader the on-chip bootloader pauses the header and then tries to copy the off-chip bootloader into SRAM and just uses our own size, and then it overwrites the on-chip bootloader stack with our return address, which is the entry point to our stub, which then takes over the execution on the PSP. For the proxy mode demo, we apparently won't have the time right now because it takes a moment to set up everything. Well, regarding that question, if we can take control, we could also then just patch the off-chip bootloader, for example, to do whatever we want. So it might continue, and then we might be able, at least on EPIC systems, for example, to to then lurk in the background and respond maybe to a special write in DRAM and then do some stuff if the x86 CPUs poke that specific address. On Risen, it's a bit harder because the CQRS takes over the SRAM, and we don't have that much knowledge about CQRS right now.
Yeah, but as for security measures, as we have now code execution on the PSP itself, in theory, there's nothing that can stop us from doing anything we want with the system, because the PSP is the root of trust for the whole AMD CPU. So if that is taken over, it's game over for any security feature later on.
So regarding the evil mate attack, yeah, you just need to flash the SPI image onto the on the main board, and then you can get access to the PSP, at least for the first generation Zen and also Zen Plus systems. So yeah, you could put some backdoor onto the PSP. We didn't had a look at the Tegra exploit for the Nintendo Switch actually.
Yeah.
But thanks for the hint. We will have a look at this later and then see what kind of similarities they share.
Similar attacks for AMD CPUs or in general? I mean, probably in general there are similar bugs, but I mean,
Intel ME, for example, had bugs in the past which allowed third parties to gain code execution on their embedded ME engine. And for a lot of smartphone trust zones, which are mostly based on ARM, and there were also a lot of similar things in the past where you could take over the boot process and then put your own code into the trusted context of the CPU. The SPI flash is actually on the mainboard because the motherboard vendor has to supply their own UEFI image because they tailor towards their own hardware they built on the mainboard. But the off-chip bootloader and the on-chip so the on-chip bootloader is baked into the CPU itself. So that is always vulnerable if you have an affected CPU. And the off-chip bootloader is supplied by AMD through their AGESA code block and is then integrated by the firmware vendors. So if you have a bug there, you will probably have a bug in all the other mainboards which share the same version of the AGESA code. So
yeah, I think our time is almost up, but Alex and I will be reachable through the Black Hat system, I believe. So if you have any further questions, feel free to ask us. And if you try out emulator and find any issues, please file a report on GitHub. That would really help us in developing this emulator further. So the thing is, the SPI has to be. What we do is we flash our own code on the SPI attached flash chip. Now, if you can protect that, put it in a case or something, well, there is some protection there, but it's a physical protection, right? If you can again access the SPI bus, which is then used by the CPU, then you can mount this exploit.
And there is no rollback prevention for the firmware as of Zen and Zen Plus. For the Zen 2 also?
Not too sure. I don't think so, actually.
So you can always flash a vulnerable version of the AGESA code and then get access on the PSP itself. Okay. So thanks again for joining our talk. And if you, as Robert already mentioned, if you have any questions, feel free to contact us through the Black Hat website, and we will then respond.